So today we're going to continue talking about vector functions, and we're going to talk about some different things we can compute to learn about the shapes of these vector functions and so on. So let's see here. We're learning arc length with parametric functions. So thinking back to what we did back in Calc 2 and also Calc 1 for that matter. When we were doing arc length and parametric functions, we found that to calculate the length of the curve, and again in parametric, x is given as a function of t, y is a function of t. The formula we used was s equals the integral from a to b, where a and b were those t values, square root of f prime of t squared plus g prime of t squared. So we took the x equation, squared it, took the y equation, squared it. Well, this is no different. Certainly parametric equations, back in Calc 2, we could take those two parametric equations, put them together into a vector. So the x component would be the x equation, the y component would be the y equation. So it would be the exact same formula if we were finding the arc length of a vector function. Okay, so if r of t is equal to f of ti plus g of tj on the interval from a to b, we would do the exact same thing. We would put the set up the same integral. And then, of course, if we're in 3 dimensions, now we've got a third parameter or a third component to our vector, and so on. Now, because we're thinking of this as a vector, it is interesting to observe that that square root that we're integrating is basically just the magnitude of a vector. Specifically, it's the magnitude of vector r prime. So another way to think about this would be that it is the integral from a to b of the magnitude of the r prime vector, because of course the vector for r prime would be f prime, g prime, h prime. So same idea. Okay. Now, I don't think there's any real advantage to expressing the arc length as the integral of the absolute of the magnitude, but it's just interesting to observe. So just to practice this a little bit, let's find the length of this curve. R of t equals cosine ti plus sine tj plus tk. As we go from the point 1, 0, 0 to the point 1, 0, 2 pi. So arc length, just a reminder, we do use the lowercase s for arc length. I don't know why, we just do. Is going to be the integral square root of, so we're going to need derivatives. So the derivative of the x component would be negative sine t. And then we're going to square that. The derivative of the y component would be cosine t. And we're going to square that. The derivative of the z component would be 1. Now we're going to square that. dt. We have not talked about endpoints. Now, in this case, it's a little bit obvious only because the z component is t. So if the z component goes from 0 to 2 pi, then the integral is going to be from 0 to 2 pi. Again, in this case, it was fairly simple because we could see that, but that will not always be the case. So we would have to figure out what is the value of t at the starting point, what is the value of t at the ending point. Anyway, clean this up a little bit. Integral from 0 to 2 pi. We get sine squared plus cosine squared, which is just 1. And then 1 plus 1, this becomes the square root of 2. Keep in mind, this is, there are a bunch of functions and stuff going on, but this is just a plain old integral. It's the integral of a function. The variable is t, and it's the integral from 0 to 2 pi. So we get t radical 2 from 0 to 2 pi. My final answer is 2 pi times the square root of 2. And I believe we talked about this parametric equation last class. This is the helix, or the spiral, or whatever you want. So basically, one run around the spiral would have a length of 2 pi radical 2. If our vector represents motion, then we can talk about what these different vectors would represent for that motion if, oh, sorry, never mind. I'm thinking the wrong slide. Scratch that. So these vector functions are the same. So let's consider this vector, the first vector r1 of t. This is t squared t cubed, where t goes from 1 to 2. Please notice that when t is equal to 1, we have the point 1, 1, 1. And when t is equal to 2, we have the point 2, 4, 8. So this is the vector function. The curve, the curve is whatever. I don't really know what the curve looks like. It's not important. But we start at 1, 1, 1. We end up at 2, 4, 8. Okay. And notice that to get from start to finish, it takes a time of 1 unit, whatever that happens to be, because we go from 1 to 2. Now, consider this vector function, R2 of u. Okay, so here are the three components. Here u goes from 0 to the natural log of 2. Notice when I plug in 0 for u, I get the point 1, 1, 1. And if I plug in the natural log of 2, I am going to get 2, 4, 8. So certainly it has the same starting and ending points. Notice that they also have the same relationship. If I take the x equation and square it, I get the y equation. If I take the x equation and cube it, I get the z equation. So the equations, the parametric equations for x, y, and z also have the same relationship, which means we are not only having the same starting and ending point, we also have the same curve. So these represent the same curve. One difference though is notice that instead of it taking us 1 unit of time to go from start to finish, now it's taking us natural log of 2 units of time to get from starting to finish, whatever that happens to be. Okay, let's try this one. R3 of W has these three components. If I plug in our endpoints again, when I plug in -1, I get the point 2, 4, 8. When I plug in 0, I get the point 1, 1, 1. So same starting and ending points, but now they're switched. So now we're going backwards. And again, we can verify that it is the same curve. Again, if I take the first curve and square it, the x component and square it, I get the y component. If I take the x component and cube it, I get the z component. So it is the same curve, the same endpoints, but now we're going the opposite direction. And notice that just like the first function where it took us 1 unit of time, this also takes us 1 unit of time because we're going from -1 to 0. So again, same curve, but now we're going backwards. And then one more here. When t is equal to 4, we get 1, 1, 1. When t is equal to 8, we get 2, 4, 8. Certainly the relationships between the x, y, and z components are the same. So again, it's the same curve. This time the difference is instead of 1 unit, it takes 1 unit of time, it takes us 4 units of time. But otherwise it's the same curve. So this same curve, same direction, but now it's taking us 4 times as long to do it. Now, again, all 4 of these parametric equations represent the same curve with the same endpoints. And in fact, we could say that these are just reparameterizations of the same curve. Parameterizing in different ways gave us different results. But the thing to notice is that to go from one parameterization to the other, we really are just doing a very simple substitution. To go from R1 to R2, we would just substitute t equals e to the u power. By making that simple substitution, I now have my new parametric equations. I could figure out the endpoints along the same lines, and so I've got my new parameterization. To go from R1 to R3, we make a substitution. T equals 1 minus W. And then, of course, for R4, same thing. We just replace the T with T over 4. So again, to go from one parameterization of a curve to another, it's really just a matter of a substitution, just a simple substitution. Okay, take one variable and replace it with another. Now, I'm bringing this up because we are now going to take a second and talk about a very specific reparameterization of the curve. So you'll notice that by reparameterizing, we can change the amount of time it takes us to go from one end to the other. We can change the direction we're going, whether we want to go, front to back or back to front. They all represent the same curve with the same endpoints, but there are these slight variations. So we're going to think about this, what's called the arc length function. Now, this is the same formula as we saw at the beginning, except that now rather than it being the number, the arc length, the length of the curve from one point to the other, now it's a function of t. Now we're going the integral from a to t. And so this would then allow me, if I wanted to calculate the arc length at any point. Once I evaluate this integral, the endpoint is t, so I'll be left with a function of t. And then if I want to find s of, I don't know, 12, I would then evaluate that answer when t is equal to 12. One small observation, it's not a big deal, but notice that the function inside now has u's and the end says du. That's not a mistake, that's deliberate. We usually try to have a different variable of integration than we have the variable that's on the endpoint. So that's the only reason why we would have the u's instead of t's. And if you don't write it that way, it's not a big deal, but that's the reason for that. So this is called the arc length function. It's going to be a function of t. And what we're going to do is we are going to reparameterize, or we're going to talk about how to reparameterize a vector function so that rather than its variable being t, the variable instead is s, this arc length function. So to help us understand, let's consider this example. Let's reparameterize the curve r of t equals cosine ti plus sine tj plus tk with respect to the arc length measured from the point 1, 0, 0. So let's start with finding s of t. So s of t would be the integral from 0 to t. Right? Notice that the point that we're starting at, 1, 0, 0, that's when t is equal to 0. Square root of the derivative of my x component, expressed as a function of u, just again to keep the variables separate, plus the derivative of the y component, plus the derivative of the z component. Oh, each of those is squared, I forgot to mention that. And it is du. Simplify. So I mean, it's the same function the same vector function we saw before, so not too big a deal. So we get radical 2 times u from 0 to t. Gives me answer of t radical 2. So we've learned, and by the way, I don't know why I usually do a cursive s, so I'll just fix that real quick. So we have learned that s is equal to t radical 2. Okay, so far I haven't done really much different, except that the endpoint is t instead of 2 pi, whatever. So now, what is it we want? We want to take the vector function that was given to us and reparameterize it. Basically, instead of it being r of t, we want it to say r of s. Well, as we said, to reparameterize a vector function, we basically need to do a simple substitution to take one variable and replace it with the other. So that's exactly what I'm going to do. If s is equal to t radical 2, doesn't that mean that t is equal to s divided by radical 2? We did all that work to find the relationship between s and t, and now we're going to substitute. Instead of cosine t, I'm going to write cosine of s over radical 2. I'm making this substitution. Sine t becomes the sine of s over radical 2, and then t becomes s over radical 2. We haven't really talked about why we want to do this. But the short answer is this. This reparameterization is nice because we said that reparameterizing changes the amount of time it takes us to travel along one portion of the curve. Well, if you have the arc length parameter like this one, it will take 1 unit of s. Nope, you know what? I take it back. Right now we don't really know why we're doing it. Never mind. Um, yeah, right now this is just something that we're working on. Um, no, I'm right. No, no, no. It'll take 1 unit of s for us to travel an arc length of 1 unit. That's exactly right. The time, in this case, the parameter is s, so that the s value, if that increases by 1 unit, then our distance will, the arc length, the distance we travel around the curve, will also increase by 1 unit. Yeah. Yes, I realize this is a video and I can probably go back and edit it, but I'm not going to bother. Okay, so we are going to talk about some other vectors that inform our understanding of the shape of a vector function. By the way, this arc length parameter will come back. There's a good reason we're doing it in this section. So the first vector I want to talk about is the unit tangent vector, r of t. So we know that r prime is going to be tangent to our curve, right? The derivative is tangent to the curve. But this is the unit tangent vector. So we're going to take that r prime and we're going to divide by its magnitude. So the unit tangent vector, big T, is equal to r prime of t divided by the magnitude of r prime of t. Right? Goes in the direction of r prime, but we're dividing by the magnitude so that it is the unit vector. Um, one of the things we're going to talk about, so t is going to come back in a minute here. One of the things we want to talk about with regards to the shape of a curve is the curvature. The curvature k of a curve describes how sharply it breaks. I'm sorry, that's not k. That's the Greek letter kappa, which I would tend to draw with the line and then a little curved sides for k, something like that. So it's the Greek letter kappa, my bad. So curvature describes how sharply something bends. So if you're right near that vertex, it would have a large curvature. If you're out at the edges where it's straighter, then we would have a very small curvature. Curvature is always positive. I guess it's sort of like concavity, not quite. I guess I can see how they would be related to each other, but it is not the same thing. The curvature would always give you a positive value. The question we're now going to ask is, how do we calculate the curvature? And there are going to be a few different ways of answering that question. One way is the curvature of a curve, kappa is equal to the magnitude of the derivative of t with respect to s, where t is the unit tangent vector and s is the arc length parameter. This brings together the things we've been talking about, the arc length parameter and t. So notice that in order for us to even talk about this, t would have to be a function of s. Well, the only way for that to happen is that r would have to be a function of s. So in order to do this, in order to use this formula, number one, you would have to reparameterize r using the arc length parameter s. You'd have to change the function r to be a function of s using the substitution like we did earlier. Then you can find t, because t would be r prime divided by its magnitude. We talked about that a minute ago. There's t. And then the curvature says, okay, now take the derivative of that with respect to s, because t is a function of s now. And then this says, okay, now find the magnitude of that derivative, because of course t is a vector. So we can find the magnitude. So the derivative would be a vector, and so we could find the magnitude of that vector. Okay, so clearly this is an involved process. We need a better way of doing it, because that just sounds like a giant pain in the neck. So there are other ways of computing curvature. One of them, your book refers to Formula 9. An easier formula would be this one. So curvature can also be found as the magnitude of t prime of t divided by the magnitude of r prime of t. The nice thing about this formula is they are both functions of t. We no longer need to worry about the arc length parameter. So that step at the very beginning we can skip. Now we just have to find t and its derivative. Notice that both of these are magnitudes. And so this is one way to do it. So let's take a look at an example where we're doing just that. Let's find the curvature of the circle with radius a. Well, to do this, step one, we need to parameterize the circle. We need to find r of t. I would point out that on a circle, the radius is constant. The radius is a. And so we could actually use polar coordinates, r cosine theta and r sine theta, but we don't need r because r is constant. It would just be a. So I'll do a cosine t, comma, a sine t. But instead of theta, I'm using letter t because that's our variable. I mean, you can do theta. It just doesn't matter. The parameter can be called anything. So there's a. Excuse me, there's r. Let's find r prime. So r prime would be negative a sine t and a cosine t. Let's find the magnitude of r prime. It's not a vector. So that would be the square root of a squared sine t plus a squared cosine t. Factor out an a squared. Square root of that is just a. And then we're left with sine squared plus cosine squared, which is 1. So the magnitude is 1. Okay, we know t is r prime divided by its own magnitude. So that would be negative a sine t, comma, a cosine t, divided by a. So the vector t, the unit tangent vector is negative sine t, comma, cosine t. Okay, now let's think about the curvature formula. Curvature formula talks about t prime. So let's find t prime now. By the way, some people may be thinking that t prime is just r double prime. Maybe you're thinking, okay, well, if t is r prime, then wouldn't t prime be r double prime? The answer is no. Notice that if I were to take the derivative of r prime, I would get r double prime, but notice there are going to be some a's in there going on. But because t divided by that a, it changes things. What if the magnitude of r prime had not been a constant? What if it had been some other function? Then when I find t prime, I need a quotient rule because then t would have some other function multiplying on the bottom or dividing on the bottom. And so now when I find t prime, there's a quotient rule going on. So there's a lot more to it. I guess what I'm trying to say is t prime is not the same as r double prime. I can see where people might think they're sort of related, but they're really not. They're not the same thing. And certainly finding t prime is a lot more involved than just r double prime. R double prime is saying, okay, here's r prime, take its derivative again. That one's fairly straightforward. Anyway, t prime would be negative cosine t, negative sine t, and we need the magnitude of t prime, which would be the square root of cosine squared t plus sine squared t, which would just be 1. Finally, curvature is equal to the magnitude of t prime divided by the magnitude of r prime So it'd be 1 over a. Remember, a is constant. A is the radius. So this formula kind of makes sense. It's a circle. Wouldn't it, because keep in mind, curvature could be a function. There could be t's left in my answer here. But in this case, we got a constant answer. Kind of makes sense because it's a circle. Of course, the curvature is the same everywhere. So we got a constant answer. Also notice that if I let a get bigger, meaning I let my radius get bigger, the curvature gets smaller. So a circle with a larger radius would have a smaller curvature because it's not curved as tightly. So it kind of makes sense that there's this inverse relationship between radius and curvature. All right, so this is one formula for curvature. There are others. Here's one here. You can also find the curvature using this formula. By the way, I don't expect you to memorize which is formula 9, which is formula 10, but when in the homework, it refers to them, so I just want to make sure you know what they are. The book calls formula 10. Magnitude of r prime cross r double prime divided by the magnitude of r prime cubed. I personally, if I had to choose between formulas 9 or 10, this is the way I would go. I just find it a little more straightforward. Don't have to worry about finding t or any of that stuff. So if you want to do that, you can use this one. Really, I would just memorize one of these two formulas, and it really doesn't matter which one you use. But again, I personally am partial to formula 10. All right, so just to see an example of this, find the curvature of the space curve, r of t equals t squared t cubed at any point t. What happens to the curvature as t goes to infinity? Okay, to use the formula, we need r prime. So that would be 1, 2t, 3t squared. We need our double prime, which would be 0, 2, 6t. We need the magnitude of r prime, so let's throw that out here right now. That would be the square root of 1 plus 4t squared plus 9t to the fourth. We need r prime cross r double prime, so let's do that real quick. So ijk, 1, 2t, 3t squared, 0, 2, 6t, and let me just quickly do this here. So it would be 12t squared minus 6t squared, so 6t squared, negative 6t, and 2. So I went through that fairly quickly, but you guys can take time and work through it. We need the magnitude of that. So magnitude of r prime cross r double prime. So that would be the square root of 36t to the fourth plus 36t squared plus 4. And so my formula says that kappa is equal to the magnitude of the cross product divided by the magnitude of r prime cubed. So that would be 9t to the fourth plus 4t squared plus 1, and that would be all to the 3/2 power. Now, there's a little simplifying you can do. Actually, the top simplifies fairly nicely now that... No, it doesn't. No, it doesn't. You can pull out a fourth. That's about the best you can do. But this is a fine answer. There's no reason to keep going at this point. This is a good answer for the curvature. It does ask what happens as t goes to infinity. So it's worth mentioning that as t goes to infinity, this would approach square root of 36t to the fourth on top. The bottom would be 9t to the fourth to the 3/2 power. So the top would be 6t squared. Basically, I'm just looking at the biggest power of t on the top and the bottom and ask what happens. The bottom's going to be 27t to the sixth. It doesn't matter what it turns into. This turns into, well, basically approaches 0. So this tells me that as t goes to infinity, as we let time go on forever, this will flatten out. Basically, this will become as close to linear as it can get. The curvature will approach 0. Okay, so we got two formulas. There's one more formula for curvature I need to share. This one's fairly specific. If you're looking at a plane curve, and if that plane curve can be expressed as y equals f of x, then we can use formula 11. And formula 11 says the kappa is equal to, now, on the top there, that is absolute value. That is not magnitude. Because, of course, f double prime is f double prime is just a scalar. So it doesn't make sense to take the magnitude. So it's the absolute value of f double prime of x on top, and then all that stuff to the 3/2 power on the bottom. Now, if you're curious where this comes from, it comes from basically taking that scalar function and creating a vector curve out of it, or a vector function out of it. If we define, not prime, excuse me, if we define r as equaling, well, in 2 dimensions, we can parameterize with just t and f of t. And then if this exists in the xy plane, then the z component would be 0. If you were to take this vector function r, and you were to apply formula 10 to it, or probably formula 9 too, I don't know. But if you applied formula 10 to it, this is exactly the formula that you would get. So just to see what this looks like, find the curvature of y equals x squared at these 3 points. So of course there's f. F prime would be 2x, and f double prime would be 2. So the curvature is equal to the absolute value of the second derivative, that's just 2, over 1 plus f prime squared, all to the 3/2 power. So if I clean this up just a little bit, I get 2 over 1 plus 4x squared, all to the 3/2. Okay. And so we want the curvature to each of those points. At the point 0, 0, let's plug in 0 for x. So the curvature is going to be 2. At the point 1, 1. The curvature is going to be 2 over 5 to the 3/2. And at the point negative 1, 1, the curvature is going to be, again, 2 over 5 to the 3/2 power. And I would point out both of those fractions are less than 2. So, and this sort of makes sense because as we saw a minute ago, at this point when x is 0, the curvature is very high. As we move away, we get a curvature that's smaller, so those fractions are smaller than 2. And certainly this graph is symmetric, so the two sides that are opposite each other should give you the same curvature. All right, there's one more vector we need to talk about. We've talked about vector t, which is good. So we know that t is equal to r prime divided by the magnitude of r prime. Which means, of course, that the magnitude of t is equal to 1. It's a It's a unit vector, so its magnitude is 1. Now, let's think about what we learned last class. There was a property that said, um, that if the magnitude of a vector function was constant, then that vector dotted with its derivative was equal to 0. This was a result of the product rule for for dot product. So we saw that if the magnitude of a vector is constant, the magnitude of a vector function is constant, then that vector dotted with its derivative is 0. Well, what this tells me is that t dotted with t prime is equal to 0 for everywhere, always. T is unique, right? It's a unit vector, so it's dotted with its derivative is always going to be 0. And remember that two vectors, if the dot product of two vectors is 0, that means that those two vectors are orthogonal. So through this thought process, we define t at the very top. And through this thought process, we've determined that the derivative of t is orthogonal to t everywhere. And that leads us to something called the principal unit normal vector. We call that big N. The principal unit normal vector is equal to the derivative of t. And because it's a unit vector, we will also divide by the magnitude of t prime. So this is just another vector that we can calculate that tells us something about these vector functions. And then one more thing, just to add even more into it, we also have something called the binormal vector. N and t are both orthogonal. They create a plane. So vector b is the vector that is orthogonal to both of them, so it's the cross product. Now, b will also be a unit vector because t is a unit vector and n is a unit vector. We don't need to worry about that. So the binormal vector is the cross between n and t. Now, these different vectors tell us different things. T shows us which way the curve is going. So if we've got a vector, I should put this in the picture. If we've got a vector function or a curve that's going in this direction, t is tangent to that curve, and t points to which direction the curve is actually traveling. Now, I want to point out that when we found n, we didn't call it the unit normal vector. We called it the principal unit normal vector. Because if I wanted a vector that's orthogonal to this one, maybe it points out that way, maybe it points in this way. Both of those would be normal to the curve, but n is only going to be one of those two. N shows us the direction that the curve is turning. In other words, because this curve is turning to the left, n is going to point into that curve. So again, t is tangent, shows us which way we're going. N is normal, it points into the curve. And of course, there's that right angle because they are orthogonal. We just determined that. And then finally, b is orthogonal to both. Basically, if both of these vectors lie in the plane of the board, b is the vector sticking straight out of the board. Okay, so the binormal vector is sticking out of the plane, defined by these two vectors. So just to play around with this a little bit, to practice this, find the principal unit normal and the binormal vectors of this function. So there's r, we need r prime, which would be negative sine t, cosine t, 1. We need the magnitude of that, which would be the square root of sine squared t plus cosine squared t plus 1. So that would be radical 2. And so t is r prime divided by its magnitude. So that would be, basically take each component of r prime and divide by radical 2. So it'd be negative sine t over radical 2. Oops. Cosine t over radical 2. And 1 over radical 2. Okay, so there is t. So now to find the principal unit normal vector, we need t prime. So t prime would be, let's see, negative cosine t over radical 2. Negative sine t over radical 2. 0. We need the magnitude of that. So that would be the square root of cosine squared t over 2 plus sine squared t over 2 plus 0, which would give me 1 over radical 2. So n is t prime over the magnitude of t prime. So if we take all the components of t prime and divide by 1 over root 2, basically multiply by radical 2, I get negative cosine t, negative sine t, 0. So there's my principal unit normal vector. And then finally, to find my binormal vector, it'll be t cross n. So let's see, ijk. T is negative cosine t over radical 2. Excuse me, that's not right. Let's try it again. T is negative sine t over radical 2. Cosine t over radical 2. 1 over radical 2. And then n is negative cosine t, negative sine t, and 0. So let's see what I get. I'm going to get 0, so it's going to be sine t over radical 2, comma, negative cosine t over radical 2, comma, sine squared t over radical 2 plus cosine squared t over radical 2. So all this simplifies to be sine t over radical 2, negative cosine t over radical 2, comma, 1 over radical 2. Okay, so we've got our principal unit normal vector and our binormal vector. Okay, so that is the end of the lesson. Make sure you copy down the homework. If you have any questions on any part of this lesson, I will be back next class, and I'm happy to answer them.